Okay, Algebra 1, Section 3.6, proportional and non-proportional relationships. So you can see the objective there. We're going to write equations for proportional and non-proportional relationships. On your notes, you can look at and see you've got a bunch of stuff for proportional relationships, and then an example or two, and then same thing, a bunch of stuff on non-proportional relationships, and then some examples there. So the first thing we're going to do is just check with proportional relationships. So these are probably a little bit easier than non-proportional, so we'll start with them. And the first thing we have to talk about is what it is. It's a relationship that is proportional if the equation is in the form y equals k times x. So that's direct variation, which we know it's got a constant k. And we know, again, we can make that connection with k and m being slope, things like that. But if it's a proportional, if it's equation in y equals k equals x form. And then the big one here is, this is the big star we have to put, is if it passes through the origin. This is the easiest way to tell, is if you look at the graph, if you graph it and it passes through the origin, then we know it's proportional. So that's a big one there. We talked about direct variations because of the form y equals kx is a proportional relationship. Already kind of discussed that. It's useful in real world data, for example, like money, dollars per hour, and things like that. So we can use it there. And you can represent it with a table, a graph, or an equation. And we talk about this real world data stuff. Proportional reason would be like dollars per hour if you made like a flat hourly rate. But a non-proportional example may be like, say, a waiter or a waitress who gets an hourly rate but also makes tips. Or if there's another fee involved on top of the hourly rate, well, then that might be an example of a non-proportional relationship.
Aaron Stokes, please come to the main office. Aaron Stokes to the main office, please. Thank you.
Sorry about that. A little announcement there. Aaron Stokes to the main office. All right, so in this case, we've got this example. Mark's a personal trainer at the gym. He receives a bonus for every client that he sees. So when we look at this one, you know what? Let's skip ahead on this one. Let's go to this one. All right, table shows the number of miles driven for each hour of driving. So let's start with this one. You've got hours in the table, and you've got the miles in the table. Remember, you can represent it as a table as well. So the first thing we're going to do is graph this one. So when we graph this, let's just change our x and y scales a little bit. So if we're on our y's here, we're going to count by 20 here, just because that way we have enough room. So when we graph this one, if we go 1 hour, if we go by 20, it's going to be 20, 40, 50 would be about right there, give or take on my graph. 2 hours would be up at 100, so 20, 40, 60, 80, 100 would be about there. 3 hours is at 150, so 120, 140, 150. And then 4 hours at 200, 60, 180, all the way up at 200 here. Okay, so that would be our graph to first look at it. And what's the relationship between the hours and driven and the miles? Okay, so let's just kind of label our graph, what we've got here. We're counting by 20s. Our y-axis here is where we're going up by the 50, 100, 150. So this here would represent the miles. And then our x-axis here would be our hours. We went 1 hour, 2 hours, 3 hours, 4 hours, okay? So what does this represent? What is the relationship in this graph between the hours driven and miles? Basically, it's for every hour, for every 1 hour, you drive 50 miles. So that's kind of what our graph represents. Every hour we went along the x-axis, we went up 50 miles. We drove 50 miles. Okay? So write an equation to describe this relationship. Okay? So we already kind of talked about our rate of change here, it being 50, right? Our rate of change. If we're going to look at an equation, we need a rate of change. Well, we already kind of discussed that every hour you drive, you go 50. So our rate of change would be 50. And remember, in direct variation, we can say, okay, well, we know that this 50 is our k value. That's our k value because that's the constant rate of change, So if we're using a y equals kx equation, well, then our equation would simply be y equals 50x. Okay, where x is the number of hours, right? X is the number of hours. And our constant rate of change is 50, k. Okay? So now use your equation to predict the number of miles driven after 8 hours. So if I use my equation, y equals 50x, and I know that x is the number of hours, I can just plug that in, 50 times 8. So if you drove for 8 hours, you would get 400 miles. You would drive 400 miles. Okay? And then just one thing to check out again, does this graph pass through the origin? Does it pass through the origin? Yeah, sure. If we were to connect these dots here, if you drove 0 hours, you would go 0 miles. So yes, it does pass through the origin here. So because it passed through the origin, it is a proportional. Because it passes through the origin. So it's the easiest way to tell if it's proportional or non-proportional is if it passes through the origin or not. Okay. All right, let's talk about non-proportional relationships. Okay, so I'll highlight this one as well. Non-proportional. So the big thing here is non-proportional. All right. So a couple things we have to know about non-proportional relationships is the graph is linear. It's still going to be a straight line, just like the last graph. The only difference here is we're going to star this one too, is that the graph will not pass through the origin when graphed. So if it passes through the origin, proportional. If it doesn't pass through, then it's not proportional. So there's going to have to be something else. So to write an equation here, there's 2 steps you can do. For one, you can do either of these steps. If you're good at it, if you know how to do it, and if you're pretty good at it, you could do that. Or you could do this third step. So we're going to kind of work through the third one just because I think that's where most people will be. But the other way is if you can just identify the slope and then find the y-intercept, that's an easy way to write the equation. Okay? Or what we could do here, and we're going to do this one, is test a point for an xy and adjust. Okay? And we should put another bullet here that we're going to start with our y equals kx equation. So we start with y equals kx, and then that last point here, we're going to test a point xy. And so when we test, we're going to put a y in here and the x in here, test a point, and then adjust our equation based on if that's true or not. So we'll show you how to do that. Okay? So let's do this example here. Right? So write an equation in function notation for the graph. That's what they want on this example, is an equation in function notation for the graph. So we know that we want to start with y equals k times x. Okay? And we also know that, we've talked about this before, that it's the same thing as y equals mx, where m is your slope. Okay? And the only difference here is we're going to have to add something. We're going to have to do the adjusting. We're going to have to put something, add or subtract something here to adjust it, because it's not going to be kx, because we know it's not going to go through the origin. So we have to do some adjusting. All right? So the first thing we're going to do is we're going to take a look at this graph here, and let's try to find our slope if we can by just using rise over run. Okay, so if I just want to use rise over run here at the graph, if I go from this point here up to this point here, so if we look at the points, it looks like the y-axis is going up by 2, 2, 4, 6, 8, 10, 12, so it's going up by 2. So this dot here is at a 1. So if I was to go up, I'd probably be going up 3 and then over 1. And then I'd go up another 3, it looks like, from 4 to 7 and over 1. And then up 3 over 1. Okay, and continue with that. So it looks like my rise over run, by looking at the graph, I'm rising 3 and I'm running 1. So my slope with rise over run would be 3. So I could start with that with my y equals kx here and say y equals 3x, because my slope, we know my m value is 3. Okay, so I can start with that. So I already know my slope there is 3. So that's the first part. We got that down. We're good there. But now we have to do some adjusting, okay, because it doesn't go through the origin. So when we do that, we're going to have, and I'm just going to kind of put another highlighted area over here, just because we're going to have to do some adjusting over here eventually, because it doesn't go through the origin, right? So we take a look at that. Let's do that test notation first. Let's do this step back here where we say we're going to test a point x, y, and adjust. And then we'll work on the finding slope and y-intercept one, but test a point first. So we'll do that one first. So we can take a point that's on this graph here and test it with this equation. Then we can adjust to see if it's true or not. So let's look at this point here. Looks like this first point right here is 1, 1. Do we agree that that's 1, 1, 1 on the x, 1 on the y? So that's an easy point to use because 1s are easy to multiply. So we're going to plug in a 1 for our x and a 1 for our y. So when we do that, we're going to get 1 equals 3 times 1. Well, not right. I mean, if we take a look at that, that's not correct. We know we're going to have to add something. So I'm going to add this, and again, put my little highlighter here because I know I'm going to have to add something to adjust. I'm adjusting here. I'm adjusting for it not going into the through the origin. Okay, and so how am I going to adjust? I'm going to look and see how true this is and what will make it true. So if I continue adding this out, I've got 1 equals 3. Well, that's not necessarily the case. We know that's not true. 1 does not equal 3. So what can I adjust? What can I add or subtract here to make it that true? Okay, so 3 plus what would equal a positive 1? Well, in this case, it's a negative 2. 3 plus a negative 2 would equal that to 1. Now it works out true. 1 equals 1 because 3 plus negative 2 is 1. Okay, so this was our adjustment. This is what we made. We have to adjust it by negative 2. All right, so our equation now, we can start with that first part of the equation, but our equation would be y equals 3x. That's the same, but now the adjustment is minus 2. Okay, and finally, they wanted it in function notation. It says right here, function notation. So that's simple. We can just kind of change the y to an f of x. F of x equals 3x minus 2, and away we go. Simple as that. All right, next example. Oh, and I did talk about how we were going to talk about this part here. We're going to say, hey, identify the slope and find the y-intercept. Okay, so what is the y-intercept here? This might be an easier way if you can get good at this. We already identified the slope as 3, but the y-intercept is where it crosses the y-axis. Well, where does this graph cross the y-axis? Crosses it down here at negative 2, and that's our y-intercept. So if you can identify that, it makes things a lot easier because negative 2 is what we are adjusting here to our equation. So that's the other way to do it. All right, so now example 4 says write an example in function notation for this table. So they give us a table. This time they didn't give us a graph, so we're using the table here. So the first thing we want to do is let's take a look at that change and what's happening with the graph. Okay, so we want to find the rate of change. So we want to find the rate of change here, or basically we're looking at slope. What's the slope? How do we do that? So we're going to try to find the change in y over the change in x. Remember, y, rise over run is change in y over the change in x. All right, so what's happening to y here? I think this is non-proportional because if you look at it, our y values are going down, and you can see the point 0, it's not 0, 0 here. So what's happening to our y's? We're going backwards 1, it looks like, right? From here to here, we're going minus 1. From here to here, we're minus 1. Here to here, minus 1. So the rate of change in y, we can look at and say, well, that's negative 1. Okay? And our x's, it looks like it's going positive 1. Plus 1 here, plus 1 here, plus 1 here. So our rate of change for x is a plus 1. And again, looking at this point, 4, 0, that tells me that's not going through the origin, because that would be 0, 0. All right. So our slope here, negative 1 over 1, then we can reduce that to a negative 1. So our slope we know is negative 1, or our rate of change is a negative 1. Okay, so using that equation now, I'm going to take this y equals, and I've got my slope, my m, negative 1x, because this was my m value, right? That's my m value. And then I'm going to have to adjust it somehow. Okay? I'm going to have to adjust something. All right? So looking at it, when I look at the equation, what am I adjusting? So I'm going to go back over here and say, all right, if I use this equation now, y equals kx, that's what I want to start with, or y equals mx, or kx, doesn't matter. So I'm going to plug in the slope. Y equals negative 1x, but I'm going to have to adjust it. Remember, I know that I'm going to have to do something here because it's not going to go through the origin. Right? I'm just going to get rid of this for right now. We'll come back to that because we're at the negative 1x over here. So if I continue this equation, what's going to make this true if I plug in an x and a y? So I can use any point here, and I'm just going to use this one here, 3, 1. When x is 3, y is 1. So I'm going to plug in my 3 for x and my 1 for y because I'm using those points. So if I go 3 equals, and this one we kind of have to use the point one because we don't have a graph. We can't find the y-intercept. So this is why we have to pick a point. And so I'm picking, again, 3, 1 here. So x is 3, excuse me. So I'm picking 3, 1. So my y is 1 here. And it's going to be negative 1 times my x value of 3. Okay? And then I'm going to have to adjust it to something, right? We know it's going to be something over here that I'm adjusting to because it's not going through the origin. All right, so let's take a look and see how this works out. We've got 1 on the left side. Negative 1 times 3 is negative 3. Well, we know that's not true. We know that's not true. So what do we have to adjust it with? What do we have to adjust it with? How can I make that through? Negative 3 plus what equals 1? In this case, it's a positive 4. So that's what I'm going to adjust it with. That now I get 1 equals 1. And that works out well. So my adjustment would be 4. So now, when I rewrite the equation, which I kind of jumped the gun earlier, when I rewrite the equation, it's going to be y equals negative 1x, and then I'm going to add 4. Okay? If you remember, my slope is my negative 1. That's what I found. Okay? That's my negative 1. Found that earlier with the rate of change. And then my adjustment here was the 4. Okay, and that would be our equation there. Y equals negative 1x plus 4. And again, they want it in function notation, so we just switch that. F of x equals negative, and we could kind of take it to make it negative x. Sorry. We don't need to put the negative 1 in, so it's negative x plus 4 would be function notation there. Okay? All right. So that is that one. We've got a lesson summary here for you. How can you tell the difference? I've talked about it numerous times, the difference on a graph between proportional or not proportional. On a graph, how can we tell the difference? And then the practice problem here is kind of two-parted here. You've got one part, if an electrician charges $45 per hour plus 50 for a house call, how much will it cost for 6 hours of work? So it's kind of like the waiter waitress. You've got $1 per hour, and then you got a $50 fee for the house call. It's kind of like a waiter or waitress making an hourly rate and getting tips. And then tell me, is that proportional or not proportional? Okay? All right. That's section 3.7 for you. Or excuse me, 3.6, proportional and non-proportional relationships. Bring your questions. We'll go to work and do some other things on it in class tomorrow. All right? See ya.